Okay, so we will talk about IP security, and similar to PGP, mail security, and the coming lectures also, mostly we are going to just tell you exactly what mechanisms we have selected and how they are done in these different areas. So for IP, the main thing for you to know is IPSec. If you have done a course on network security and don't know IPSec, then people will say, well, what else do you know? So IPSec is what we are going to talk about in this, and IPSec has three parts: AH, ESP, and IK. So those are the topics of this discussion today. So IP security, so it provides exactly the thing that you need, which is authentication, integrity, and no replays, confidentiality, and so on and so forth. These standard stuff, 4 or 5 things that every other thing provides. The advantage of IP security as opposed to the transport layer security that we talked about, TLS, is that TLS applies only to the protocol or the transport that it applies, like TCP, whereas IP security will apply to everything: TCP, UDP, SCTP, whatever you have. And the applications don't have to worry about it, because all the applications are designed to run on one of those transports, and even if they don't know security, if it goes to IPSec, they get the security. So security is at layer 3. So it applies to all transports, can be implemented in the firewall and routers. So that's what it is done, actually, mostly used for. IPSec is not something that you do in your host generally. You can do it, but it is done at the firewall. So if you have 2 firewalls connecting 2 campuses, they can use IPSec, so nobody else in between can see your traffic. So for example, here we have this campus and the medical campus. I'm sure they have IPSec line going between the 2. All right. And the transparent applications can be transparent to end users, can provide security for individual users, and so it is used for VPNs, branch offices, remote users, and extranets. So you already know branch offices, which we talked about, like 2 campuses. VPN is virtual private network, which is basically again a link between 2 sites, which in some cases this site could be just one person on one place. For example, from my home or from your home, you can do a VPN. So that covers the case of remote users. And when you are doing that VPN, you are using IPSec. Okay, so you are using IPSec almost every day. And an extranet. Extranet is actually, so there are 3 nets: internet, intranet, and then extranet. Extranet is a network which is not intranet and is not internet, which is the network with some partners. So for example, WashU might, I don't know whether it has, but might partner with SLU, and they might share some secret data between SLU and WashU, right? In that case, it would be extranet, where there is some trust but not complete trust. All right, so that finishes basically what are the features that it provides, and this picture shows the same thing again. Basically, is that you could have a firewall here and a firewall there, and these 2 firewalls could talk through the internet. How? Because they have IPSec header. All right. So with the IPSec header, this thing is totally encrypted. The payload is encrypted, and IPSec header will allow the other side to decrypt that. So all the information for decryption is in the header here, and on the top of that we put a regular IP header. So the routers in the public internet don't need to worry about that. They just see the standard IP header. All right. It comes here. This device will decrypt this thing, and it will get back the original packet, and other people in the company can use it. And similar thing applies to a remote user. Like if you're connected from home, you will do this job of this firewall here, and your computer will read the IPSec header and decrypt it or encrypt it as needed. Okay, so at least the context is clear where IPSec is used. Okay, all right. So there are three parts, as I said. The first part is IKE, and IKE is Internet Key Exchange. So as the name indicates, this is used to basically somehow get a shared secret so that we can encrypt the data that has to go through the IPSec. And so that is the protocol. IKE is the protocol, but it uses some database. So every time you get a secret, you want to remember that in a database. And so there are two databases. First is the database of associations. So these are the secrets, and the basically, so if I have, let's say, five connections going on, then I will have in this database the information about those 5 associations, as we call them. Okay, 5 associations are like 5 connections. All right, and then there is another database, which is the policy database, which is more of a longer term policy issues. So the university might have certain policies about who can connect, how they can connect, what encryption technique can be used and all that. So that will be in this policy database. So this is very static database, SPD. All right, and this is very dynamic database because this is done for each connection. All right, now the connections are one directional, in the sense that when you have a 2-directional connection, that is 2 associations. So each association is one direction. And so that is the key issue. Now it says ESP protects data. I should have said, or the picture should have said ESP or AH, because AH is another one. AH is, we will talk about that in the next slide. So we'll go back to the previous slide. It doesn't go back to the previous slide. Okay. So IPSec protects the data in that sense. Okay. So again, let's see. The key components are IKE, AH or ESP. Those are the 3 protocols. Then there are 2 databases, 5 things. All right. So security associations. We have already talked most of it, but let me just go through one more time. So each host has a database of security association, but security association is one-way relationship between the sender and the receiver. And if you want 2-way relationship, you need to have 2 assays. And the reason they use one way is because the requirements on the 2 sides may be different in terms of required confidentiality or privacy or something like that. Just to allow that possibility, they don't require that you use the same method both ways. So you have to have 2 assays. And each association has a number which is called SPI. Security Parameters Index. So that is just a number. So when you talk to somebody, you say, well, this is SPI number 1, that is SPI number 2, that is SPI number 3. Just a number, right? And for each security association, you will have the destination address, obviously, and the protocol identifier. You can either talk to them AH or ESP, and I haven't talked about AH and ESP, so that will come up later on, but those are the 2 options you have. And so the database will contain SPI, the sequence number counter. So each association has a number of packets going through, and each packet has a sequence number. So that counter goes here, and the counter overflow flag, and every time you have any counter, you have to decide what to do when the counter overflows. And this is not this in this situation. Any networking situation, if you have 8-bit counter or 32-bit counter or 64-bit counter, they are going to go and overflow at some point. Right? So there are 2 decisions, 2 decisions we made. One is, do you want to get stuck at the top, or you want to roll over to 0 again. Right? And Obviously, in this case, it doesn't help to get stuck over at the top. There are situations in which it helps to get stuck at the top. But in this case, basically you roll over, but you remember that I rolled over so that, when packet come, whether they're packet number 5 or packet number 5 million, you know that they're in the same window. Right? So there is a tag here. There is a flag here. This is the counter overflow flag. Anti-replay window. And that is exactly what I said, is there is a window over which I will accept the packet. Any packets which are outside the window will not be accepted. AH and ESP information, lifetime of the SA, and mode, whether it's transport or tunnel or wildcard. So we haven't talked about these modes, which we'll talk about in the next slide. And AH and ESP we haven't talked about. And path MTU. And finally, MTU is the maximum transmission unit, how much biggest packet the routers will take. So those are the information kept in the database. In the database, we keep the index number, we keep the counter, we keep the destination address, and the protocol, and so on and so forth. So that is what we keep in the SAD. It was called SAD here, Security Association Database. Policy database, on the other hand, has things like what protocol is being used, what is the local IP address, port number, remote IP port, and so these things. So this one is used to filter the packets. Basically, if the packet comes to the firewall will match the local IP, local port number, remote IP, remote port number, and the transport protocol type UDP, and then it will say, okay, bypass this, or that means let it go, or protect it, that means encrypt it, or that's it, discard it, throw it away. One of the three. Okay, and these comments explain that the reason it is being bypassed is because this is the internet key exchange. So that means that the database is just starting setting up the connection association. This one is being bypassed because it is an error message. This one is being bypassed is that this is already encrypted. This one is being bypassed because it is going to the plain internet. Nothing needs to be done. And now let's look at the other message, protect. This one says this has to be protected by ESP in the transport mode, and this one says this has to be protected in both of these are transport modes. So the other alternatives could have been AH tunnel mode, or AH transport mode, or ESP tunnel mode. So there are 2 modes and 2 protocols, so there are 4 combinations. So those could be put here. Anyway, so this is the basically what you would call the filtering database then. This is used to just filter the headers. I mean, based upon the headers, you can filter the packets and take the action. And this diagram basically shows the same thing all over again. You look at the filtering database and see what needs to be done, discarded, protected, or bypassed. If it is to be protected, then you see whether what kind of protection does it need, AH or ESP, and transport or tunnel. And then if it is not in the database, then start a new connection. Start internet key exchange means start a new association. If it needs to be bypassed, then forward the packet. Discard means throw the packet and go on to the next one. At the receiving, the similar thing is done. You look at the database. If it is in the database, then deliver the packet. If it is not, then you see if if it is a plain packet, then obviously you see whether we need to it is bypassed. If it is an IPSec packet, whether it is in the database or not. If it is not in the database, then at the receiver you just throw it away. If it is in the database, then you process the header and then deliver. Any question about that? Is it going too fast or is it clear? Okay. Alright, so let's talk about transport and tunnels. You probably already know what is a tunnel, but just for the reviewing purposes, a tunnel is needed to be dug when you want to bypass a region where this language that you speak is not spoken, or the things that you want to do is not done. And then what you do is you dig a tunnel and get out at the other side where you can speak your language. So for example, if you had IP speaking world here and IP speaking world there, but in between nobody speaks IP, then you will dig a tunnel through that piece. Another example is you want to send a letter from here to let's take a European country, let's say Germany, but somehow it goes through Russia. Alright, and obviously Russians don't speak English. Well, that is not true, but just for the time example, you don't speak English, so how do you send a letter which has an address in English? Right? What you do is you take the packet arrives at the Russian border. Over there some American agent takes the packet, or just before the Russian border, the American agent takes the packet, puts into another envelope and writes the Russian address of the exit port. So the packet goes through Russia in Russian. At the other side, another agent throws away the envelope and the packet continues in English. Make sense? Same thing we do here. Whenever we want to go through anything where the protocol is not understood, we take the original packet, put it inside a new header, and this new header is understood in that foreign world, and then the packet, this header is taken off at the end of the foreign world. Okay? This is called encapsulation. Right? Also called tunnel. So, and this is used for any feature, any new feature that comes up and the old router may not understand it. So how do you handle it? Well, if the old router does not handle it, you go through tunneling or encapsulation. Okay? So the same thing has to be done, I mean basically similar technique we use here in IPSec. In IPSec, we take the original packet with the header and put it into a new protocol and then put that into the IP header, a new IP header. So this IP header says that my payload is AH or ESP. Okay? And AH or ESP basically has all the information here, this header, and then that allows you to decrypt this. This dot means this is all encrypted. Nobody can look at that. Okay? Now, so AH is called authentication header, and all it does is it authenticates the data and the origin. It doesn't encrypt. It only guarantees that the data came from X and that the data was not changed. Alright, it does only authentication and integrity, but not the encryption. ESP does everything. ESP does confidentiality, it does the original authentication, it does integrity, and it does anti-replay service and all that. So ESP is in some sense doing more than AH, and why in the world they decided to have two separate protocols is beyond me, but that's what the case is. And so you have AH and ESP, and so AH does only one part and ESP does integrity and authentication. Now, there is one more option here. It says that the original IP header is encrypted optionally. So in some cases you may not want to send the original IP header. You can just throw it away before sending, and then the receiver can reconstruct that from the outer header. Okay, and I will show you those situations. So that makes for two modes, tunnel or transport. And the difference between the two modes is whether the difference between two modes is whether the original header is there or not inside. Okay, so let's see that. Basically, there are two situations. One situation is where the one user wants to talk to the other user end-to-end security. Alright, in this case, the original header will be put inside and sent through these routers to the other side, and that would be called transport. Okay. On the other hand, these users may not do anything, but there are routers on the way that can encrypt the packet for you, and this can decrypt the packet for you, and so that would be the tunnel mode. So let me see. I may have said something slightly different. So in the transport mode, the original header is not there. In the tunnel mode, the original header is there. Okay. In the tunnel mode, original header is there. In the transport mode, original header is not there. Okay. Is that clear? So this is the original packet IP header and the rest of the packet. In the transport mode, IP header goes here, rest of the packet goes there, and then IPSec goes in between. But the original header is not duplicated here. In the tunnel mode, your packet remains as it is, and then the IPSec sends it to the gateway, to the other gateway. So this will have gateway to gateway address, and then this will have A to B address, end-to-end address. Right? So this is the tunnel, because the tunnel is being, this is like a VPN between the routers, and this is end-to-end. Yeah, go ahead.
How does the router know to reconstruct the old IP header in a telephone?
Okay, so the router doesn't do that, right? See, in the tunnel, a router only does the tunnel mode. Right? In the tunnel mode, the original IP header is preserved inside. Right? In the end-to-end mode, it is going from A to B. The routers don't need to know. It's just that is already in the outer header that it is going from A to B. Understood? Make sense? Yeah. So in the transport mode, I just sometimes get confused between the tunnel and the transport, because now it is easy to remember. Transport is end to end, and tunnel is gateway to gateway basically. And so this is like VPN mode, and this is end to end mode, transport mode. Alright, in the end-to-end mode, we already know the end, so we don't have to preserve it. It is already in the outer header. In this case, because the packet is going only from gateway to gateway, and then it will be decrypted, so we need to preserve the original one. So this is really total. The header is kept. Alright, so now we know two modes. Now the difference. Now let's see the header. The difference between the authentication and the ESP. So authentication header protocol, this is the header. The first field is next header. So it tells you what is the payload type, here. Next header simply is the payload type. And then the length, what is the length of the payload, which is not shown in this picture. This 16 bits are reserved. Then SPI, so what index it is, and then the sequence number of the packet, and then the authentication data, which could be variable number. And so that's all there is. Now this is total 32 bits, 1, 2, 3, plus whatever number here, 32-bit words are used. Now the next header value could be 6, in which case it is TCP. Next error value could be 17, in which case it is UDP. It could be 4 for IP and 51 for another AH. Alright, so these next error values are standard and not just for AH. Those are standard even if, let's say you have an IP packet, if the payload is TCP, it will say 6. In the IP packet protocol, there is something called payload type, that will be 6. UDP will say 17. So in this case, the IP packet, the outer header will say payload type is what? Anybody can think? If it is an AH packet, the outer header will have the payload type of this is an AH packet, so the outer header will have a payload type, right? And that will be 51. Right? So the IP header will tell that we don't have a TCP here yet. What we have is the next field is AH. So handle AH. Inside the AH packet, the payload type will be whatever it is, TCP. Let's say it is TCP, then we'll say TCP. If it is not TCP, it could say ESP. I mean, you could encrypt inside encrypt. You could do whatever you want, right? So for every header, there is a payload type, and that tells what to do with that payload, right? So here AH type 51. Okay, now next interesting thing to notice is next header. They don't call it payload type, they call it next header. Has anybody heard that word before, next header? Anywhere in any course in networking? There is a IP version type which uses next header. Anybody remembers that? Huh? IPv6. Yeah. In IPv6, they have many headers. They don't have just one header. Even for IP itself, they have many headers. And each header has the next thing as a payload type, and they call it next header. Alright. So the people who designed this AH, you can see their background. They are coming from the IPv6 world. This is coming from the time when IPv6 was really, people were looking forward to it. So they call it next header, and otherwise it would have been called payload type. Actually, originally they said that we are designing security only for IPv6, let IPv4 turn over, and then come to IPv6. But IPv4 didn't turn over. They just said, okay, we will just call it, we'll just use it as it is. So IPv4 uses this AH as it is. So there is no reason to go to IPv6 just for this. Alright, so let's see. So the payload length is, now here is another kink, is the length of AH in 32-bit words minus 2 for IPv4, length of the AH in 64-bit words minus 1 for IPv6. This is really crazy. But this is throughout the IP world, that there is no unit of length. Every protocol defines how they will count. They could have just taken bytes everywhere, but no, somebody counts in bytes. Some protocols count in 2 bytes, some protocol count in 4 bytes, some protocol counts in 8 bytes. So you have to remember when you see a length field as to what unit it is. Alright, now here they have 2 different units for the same protocol depending upon whether it is IPv6 or IPv4. IPv4 counts in 32 bits, IPv6 counts in 64-bit, and therefore whichever religion you belong to, you count accordingly. But you have to subtract 2 for IPv4 and 1 for IPv6. And I can't guess why. But anyway, you see the length field and then you adjust the length accordingly to find how many bytes to expect. SPI is the index as we said about, and then it is authentication data. At least it could be in most packet would be the integrity check value, which will be basically the integrity check value like CRC or whatever I want to say it, so that if there is any error, the ICV will not match. And yes, that's all there is. Basically all there is the ICV, and with that ICV you can be assured of several things. What you can be assured of is that the data has not changed, and that none of the header fields in the payload have changed. And actually this ICV will cover all of these things. So none of these things have changed. Alright, so you can be assured where the packet came from. That's how it does the original authentication, is because all these fields are covered by ICV. So SPI is 32-bit words, of which 0 is reserved for local use and 1 through 255 are reserved for future use. So the number cannot be 0 through 255, and it can be any higher number from that point onward. So that gives you how many total SPIs can you have. I don't think you will ever run out of SPIs before you run out of your compute power. So 2 raised to 32 minus 256. Okay. Any question about the header? If not, let's see ICV coverage. ICV covers the whole packet from outer to inner, the whole thing, and the header. If any of these fields change, ICV will not match. So the problem is that some fields do change. For example, in the IP header there is a hop count field which is decremented at every hop. Time to live, it's called TTL. Right? It changes at every hop. So that is not included in the ICV. Okay, you zero out that field before you do the ICV. And in fact, every field in the IP header is divided into 3 types. Immutable, that means it will not change. For example, the destination address should not change, the source address should not change, and packet lengths probably should not change. Well, packet length probably will change, but so there are many fields that will not change. Okay, those are called immutable. Then the other side is mutable, the one that can change. Now, out of those, we divide into 2 categories. Predictable means we can tell you what the field value will be at the end. Are not predictable, right? So the predictable is the value intangible are predictable that can be predicted at the arrival. So source address is immutable, destination address with source routing is mutable but predictable. So what is source routing? With source routing, you can put a number of intermediate destinations in the packet. So you can say from here you want to go to Germany, I want to go from here to New York, from New York to some other airport, from there to there to there to there. So you put all these addresses in the source route, in the packet. Alright, so the packet has, let's say, 5 destinations. And there is a pointer which says, okay, now we reach the 4th destination, the next is 5th destination. Right? So when we reach the final destination, we know if the packet reaches Frankfurt, it will be pointing to the 5th address, and so that is the final pointer. The pointer value would be 5 at that point, even though it is 1 at this point. Right? So that is predictable, mutable but predictable. Alright, so you divide the into 3 categories: immutable, predictable, or unpredictable. Unpredictable is the one that you will not include. So the AH header So basically these unpredictable values are set to 0. So the AH header, the next header, payload length, reserved SPI, sequence number, and authentication data is set to 0 for and explicit padding bytes if any. Everything is covered here except that when you compute ICV, at that time you put the ICV value to 0 and compute the ICV and put it in there, and then at the other end you basically, normally things are arranged so that you can just leave it as it is and the ICV will come out to 0. So the upper layer protocols, data which is assumed to be immutable in transit, so all that is covered, right? Now, so one of the homeworks actually which is at the end of this lecture is for you to look at all the IP fields and classify them into these three: immutable, predictable and unpredictable. Okay, so it's important that you understand the three things as to what this means. Is it clear what is immutable means and what predictable and unpredictable means? Alright, so now we are in AH version 3. Version 2 came out in 2005. Sorry, version 2 came out in 1998, version 3 came out in 2005, and version 1 came out in 1995. And so version 3 has made these changes. First of all, SPI is now has a uniform algorithm for unicast and multicast. So regardless of what kind of packet it is, SPIs can be handled correctly for both. For unicast, you can just use the SPI to find the association. In the case of multicast, SPI and the protocol can be used to find the association. And then obviously we'll add the destination address, source address, and so on and so forth. Anyway, I don't know what uniform means, but basically they clarified exactly how to handle these SPIs. Extended 64-bit sequence numbers for high-speed communications. So the sequence number as shown here in this previous slide was 32-bit. Now they allow you 64-bit, and I'm sure there is a bit in the header someplace which says that there is in 64 or 32. Anyway, and then separate RFC for mandatory algorithms. And then there is an RFC which indicates that everybody has to implement these particular encryption, hashing, integrity algorithms, because problem is if you leave the field open, then somebody can get to you by just putting nulls in those places and then somehow use that information. So minimum required is that, so there are some minimum required algorithms which everybody has to implement, and people can implement the stronger ones, but they may have to accept at least these minimum ones if they want to. Alright, so much about AH, just actually 3 slides. So the AH only does is ICV, and ICV, integrity check value, covers the whole packet except for those fields which are going to be changed and but cannot be predicted. For example, a good example is time to live. Time to live, we cannot predict what the value would be at the destination. Alright, so the next protocol is ESP. ESP is provides everything: confidentiality, authentication, integrity, anti-replay, even traffic flow confidentiality, limited traffic flow confidentiality. So traffic flow confidentiality, I think we have discussed this before, but let me just explain again, is that you don't want people to know how many packets I sent. So I may send some packets which have no information in them, or I may make the packets bigger than what they are, right? So you cannot just say, well, this is only a short one-word bomb. It could be big message. So So that is allowed by this, and the technique is very simple, basically by having padding. Services depend upon the option selected when you establish security. And net location can use a variety of encryption authentication, and rest of it basically, it specifies all those algorithms for those. So the packet itself starts with SPI, sequence number, initialization value, IV. Now this is different from ICV. ICV is here. IV, anybody knows what IV is used for? Anybody remembers what IVs are used for? Yeah, see, when you do encryption, you remember the block mode encryptions, and you were doing chaining, then you want to start from the beginning, that is the IV. Alright, payload data, and they decided to put the next header at the end. Can you believe this? And the ICV is at the end. So anyway, the next header is not up front, it is at the end. So this is the payload type, which doesn't make sense to me, but anyway, that is where it is. This is after the payload. But anyway, they get the whole packet, then only they can process it, so it doesn't matter where they put this stuff. But generally we expect to see things in the front, but here in this protocol they have the next header here, pad length is here, padding is there, and then TFC padding. So TFC padding is the traffic flow confidentiality padding. That is the padding you put simply to extend the length, not because you want to make it a multiple of 64 or 32. The second padding is to make it multiple of whatever. Actually, it looks like it is multiple of 256, because you can have a padding up to 255 bytes. Yeah, go ahead.
From the beginning of the initialization value to the end of the rest of the payload data.
Okay, no. Okay, so here the thing. First of all, the payload starts from here. This is where the IP header might be. If you have put the original IP header, internal IP header, that will be right there. Okay, and the original IP packet's end will be here. So that is the original IP packet. If there was no header, then the original IP payload will be there. All right. Second thing is, you should notice these things on the side. It says payload is from here to there, right? So that is your question was that why the IV is part of the payload? Is that the question? Oh, okay. All right. Yeah. That is actually, a misdefinition in my view, and this is my personal view. I think this is really the thing that came from the higher layer, which is the IP layer. In this case, the higher layer is IP layer. And so that should be called the payload. This was added by this header, this layer. So to call this payload is not, and similarly to call this padding as a payload is just arbitrary in my view. Actually, really the payload is this. And the thing to notice is that all this part is encrypted. Okay, but somehow the figure in the book has this wrong color for this one. You see, IV cannot be encrypted. Right, you need IV for decryption. So it says here encryption, and the arrow ends here. So this is not encrypted, but when the color person made a mistake here and coloring this thing, it should be clear. So the IV is not encrypted, and in my view, this would be called the payload, but the padding and the IV would be part of ESP, strictly speaking, but the book has the arrow indicated here as a payload. But really, this is the payload. Next header, okay, now pad length in bytes, and then the next header is TCP, UDP, whatever. Authentication data includes ICV. There are several errors in this diagram, let me tell you. I'm noticing another error. This arrow, ICV coverage, has to go up to here, because ICV always protects itself. CRC always protects itself. Okay, you cannot design a integrity check value where you can change the integrity check value. Right? So if I were to redraw this diagram, I would not put a color here. I would make this arrow bigger. This thing looks okay. The payload I may have to change unless I want to start calling this padding as a payload, which could be acceptable somewhat. But to call IB as a payload is not acceptable, it is not to me. But this is how the picture is in the book. Alright, moving on. ESP version 3 again came out in 2005 and again solves almost the same problem, unicast versus multicast, extend the sequence number, put the mandatory algorithms, and then if you want to get both confidentiality and integrity, so then it allows that combination. And then traffic flow confidentiality was added in version 3, the TFC padding. Can generate and discard dummy padding packets, next header is equal to 59. So if the whole packet was the TFC padding, then the payload is 59. Everybody understood that statement? Is that there is no TCP IP or anything here, it is just TFC. Alright, issue no version number in the header, but older versions will reject new algorithms and options. So there is a problem still that neither of the two, AH, I didn't see in the AH also the version number, and ESP does not have a version number. So when you get a packet and it is version 3 and you are at version 1, what do? I mean, you just think that the packet is misinformed or misformed. For example, the older version may not know TFC business, or they may not know that number there was 59. They may not know what to do with it. So actually throwing it away is not a bad thing, but it just happens to be coincidental. There could be some options that may not be correctly done. Alright, so how do we do anti-replay? Anti-replay, as we said, is that you keep a window from beginning to the end that you will accept. And you decide that, well, we'll keep a window of 200 packets. So even though this is the packet I got, and I'm going to, and this is the next one I'm expecting, but if something comes ahead of time, I will take these packets. And if something comes again from behind, I will take those packets. But anything before that, actually, we will throw away. So now let's see. And the window is advanced when the valid packet is received. So we have valid packets up to here. Sorry, it's not here. We have up to here, and we will take any of the next 200 packets. And if something comes up, and then the window may move up to whatever valid packet you have received, and so that there is no gap. So if suppose it's up to here, you get this one, you might move up to this one because you have received all of these. Just like the flow control window, this is the anti-replay window. And so you just keep a fixed size window and you move it as soon as you receive valid packets, and so that everything before that is valid, already received. If you receive anything out of the window, you throw it away. If you receive any older packets, you throw them away. If you receive any packets which are too far in the future, throw them away. So these packets are kept out of order in some sense, is that these white spaces are still not received and these out of order packets are being kept to hoping that we will get them and then we can move the window up. At some point you might time out and you might get a retransmission or whatever. Alright, so that is the anti-replay service. Any question about that? And actually there is a homework on that too, so just make sure that you understand. Where was that? There is a homework on anti-replay service. So basically the key is up to here we have received everything, and we therefore will accept the next W packets. We'll keep them out of order in cache. If anything comes after W, we don't have a space to keep them, so we'll throw them away. If we receive something old, we don't need them, so we throw them away. Alright, so now combining security association. So you can implement AH or ESP, and you can also implement both AH and ESP, but you will have to somehow put one inside the other. So you have to make a bundle. And actually maybe I should show you the next picture which shows the bundle clearly. So you could have one tunnel and inside that you have another tunnel, inside that you have essays, and like that. So that's a bundle. So you could do a association bundle, and you could have AH over ESP, or you could have iterated tunneling where these are the four cases just shown in the next picture. So basically all security is between the end systems, all security is between the gateways, and then case 1 is inside case 2, and then the tunnels between a remote host and firewall, and 1 or 2 essays may be in case 1. So there are 4 cases which are shown here. So first case is this one, case 1. You have a host and this is end to end, and you could have many SAs which go through this tunnel or this bundle, and so that is called case 1. In the case 1 you have end to end security. It could be AH transport or ESP transport or ESP inside AH or any one of these 3, AH, ESP or ESP inside AH or ESP. So this is basically one inside the other, but everything is end to end. So this is a straightforward simple thing. You could keep putting the tunnels inside the tunnel, which means that you can keep putting headers on the headers on the headers on the headers, end to end. So that is case 1, which is simpler. In case 2, the tunnels end at different point. So this tunnel ended here, whereas this tunnel continued to the end. So case 2, between the gateways or firewalls, single association, no nesting. So this is the second case between the gateways. Sorry, case 2 is here. Sorry, I cannot even read very well. These letters are so small. Case 2 is here between the gateways. Case 3 is this one where you have nesting. Case 3 is 1 inside 2. Case 1 end to end inside case 2 between the gateways. So that is case 3. You have gateways as well as end to end. Case 4 is tunnel between a remote host and firewall. 1 or 2 essays may be used as in case 1. So now this is the most general case, is that you have some end to end, you have some tunnels, and so on and so forth. So this is a combination of all 3. This one is all end to end, this one is all gateway to gateway, this one is gateway inside the end to end inside the gateway, and here the mixture is different than that one. So I don't know actually. I think that basically the idea is that you could be having multiple levels of headers and they could be ending at different points. They should have simply said that rather than combining these 4 cases, but that's what it is. All right. So, so the summary of this slide and the next is that you could have tunnels inside the tunnel ending at different points. Okay. Now we come to the key management, IKE. So the purpose of IKE is handshake to just somehow agree on a security or a secure key, and so basically we need 2 pairs of keys. We need 2 keys for one direction, 2 keys for the other direction, and why we need 2 keys? Because we need 1 key for integrity and 1 for confidentiality. So they use separate keys for integrity, which requires hashing, and confidentiality, which requires encryption, right? So we use different keys. So we need 4 keys for a 2-way connection. Now the key management could be manual, in which case it's not a big deal. You could send somebody the key by mail, by some other method, and or could be configured. But what is more interesting is this automated key management, where you could do it remotely, and so that's what we are going to talk about. That's what really the IKE is all about. So now there are few names that you have to understand here, and you will see them all over the literature. One is called Oakley, and one is called ISAKMP. So Oakley is the name of the key exchange method, and ISAKMP is the name of the key management method, and these are all historical. Historical in the sense that before IKE was there, or IKE version 2 was there, they had this Oakley key exchange and ISAKMP key management, and then IKE version 2 came about and they removed the names, but they use the same techniques. So every book that talks about IKE has to talk about Oakley and ISAKMP. All right. So even this book talks about Oakley and ISAKMP, but the previous book that we used in this course only had ISAKMP and Oakley. So what is Oakley? Oakley is the Diffie-Hellman key exchange. And if you remember, the Diffie-Hellman key exchange had some weaknesses because it could not identify the parties. Somebody in the middle could just may attack. So the man in the middle attack. So that is removed. And denial of service is removed by having cookies, and then several groups of pre-specified global parameters. So what is that? Basically, when you want to do Diffie-Hellman, if you remember Diffie-Hellman now, you had a G number, G, which was the global number, and you raised it to some power and you sent that value, right? Nobody can determine the power because nobody can take the log, but everybody knows G and everybody knows G raised to A, whatever number you selected, right? So that G number is a big number, and so how do you find that number? Well, everybody could go and try to factor out lots of numbers and figure out a prime number, but instead of doing that, what the world has done is they have agreed upon a certain number values, certain values. Everybody uses those values. Okay? So if you go to the RFC, whichever RFC this one talks about, it has 5 or 7 possibilities. Okay? If you want to use 512 bits, use this G value. If you want to use 1024, you use this value. If you want to use 2034, use this value. So that is what it means by global parameters. Yeah.
Is that not subject to attack by rainbow tables?
So that actually makes it weaker. If everybody is going to use one global, then you don't have to worry about I mean, trying out different things, but I mean, I'm not sure as to, I mean, basically what is required to break a 512-bit, thing like that, right? But having it random would be much more stronger, I think, than having a global value. So maybe people can just sit down and just break that and make a whole table of all the powers of all of those numbers, which will be a big table. But anyway, so that is the pre-specified global parameters. Nonsense to protect against replay. So that adds nonsense. And then DH public key exchange with authentication using digital signatures, public key encryption or symmetric key encryption. So you can even use public key encryption, which means you could use certificates. And things like that, to including symmetric key encryption if you already had symmetric key. And so somehow you basically exchange the keys. Can use arithmetic in prime fields or elliptic curve fields. So they use both. We saw the RSA, which was arithmetic in the prime fields, and we saw elliptic curves. Remember elliptic curves? To add 2 points, you had to do all this math. So all that is used here in real world. Alright, so Oakley is Diffie-Hellman in very simplified manner, okay, because it is an extension of Diffie-Hellman. Next is ISAKMP. So ISAKMP stands for Internet Security Association and Key Management Protocol. And it basically provides what to do to create new associations. So this is a protocol. And so it defines the procedure and the packet formats to establish, negotiate, modify and delete security associations, SAs. It is independent of the key exchange protocol, encryption algorithm and authentication method. So basically you could use any exchange protocol such as we talked about, public key, private key, whatever, but it has certain protocols, certain messages that have been formalized. So for example, you could send a header message, get a header response, and so on and so forth. All right, and at the end of these two messages, you will have a security association, and then you can create child security association. Is that you could create, once you have one secret established, then you don't have to go through the previous negotiation, because you already know what encryption algorithm you are going to use. All we need to get a new key. I could just pick a new key from my pocket and send it to you by encrypting it, because we have a shared secret. So creating the child message is much more easier. So in which case you just send those two messages. If you want to create the first SA, then you have to go through more what we would call the initiation, which means Diffie-Hellman kind of thing here in the beginning. So there is initialization, and then the first SA, and then the child essays. The details actually you can read in the book, and so what these different fields are, I don't think I want to go them here though. I mean, like basically the standard method of agreeing on a key. So the I packet format, SPI on two sides, next payload, rather than next header, major version, minor version. So now here they remember the version numbers, exchange type, flags, message ID and the length. So basically they don't say what the unit is. So anyway, there's a length of the message, and message ID is the sequence number. So this is actually the sequence number, and exchange type is the message type. So this one will tell you whether this is a header message, well, not header message. So these messages are different types, and it is not indicated in this picture, so I can't tell you. But basically, that goes here. The message type goes here, and this is just a sequence number. The message types could be key exchange, could be identification, could be certificate, could be a certificate request, could be authentication, and so on and so forth. So these are all different message types. All of them have a number which I have not indicated here, or the book has not indicated here. But basically that number, exchange type, goes in that field that we saw a minute ago. And the key is that there are two words they use. One is called a proposal, and one is called transform. So so you send a set of proposals for encryption, for hashing, and so on and so forth, and that's why it is a set. And obviously the response would come out a selection of that. If it is a key exchange message, then it will contain the Diffie-Hellman group number. So that is the global group number. Remember, we talked about there are 7 or 8 group numbers specified in the RFC. So you will put that this is the group number I am taking, and these are all the data required for generating the key. If it is an ID, then it will say what type of ID it is, IPv4, IPv6, and whatever the ID is. Certificate, it will have what encoding the certificate data is in, and then the certificate itself. Certificate request, this is the encoding I want, this is the authority I want. Authentication, and so on and so forth. So basically, there are many things which go on in these messages, and so the exchange type field is this. Now these are the algorithms which are required for which are allowed for encryption: 3-CBC and AES CBC, and there are two different sets, VPN A and VPN B. VPN A is older, VPN B is newer and stronger. So in the old days they used this, and now we will prefer these. Similarly, for the suite, the cryptographic suite, that means the combination, there is something called NSA suite B. So NSA has specified a set of combinations which is, there must be an A before, but now it is B, which is what is used for the government use, and that specifies these combinations for integrity, for encryption, for pseudo-random functions, and so on and so forth. So these are all the algorithms that are specified in that set. That brings us to the end of this IPSec chapter. And the 7 things that key are, first of all, that IPSec is at the IP layer, and it provides authentication, confidentiality, and the key management. And since it is the IP layer, it applies to all the traffic, all protocols, all transport protocols. Second thing we learned is that the security sessions are one way. So the reason they are one way is because the direct requirements for the two directions could be very different, and that they can be bundled one inside the other. Authentication header is done using integrity check value, which is done using HMAC. ESP uses confidentiality and integrity both. Then the SAs can be tunnel or transport. So now let's just remember transport means end to end. Okay? And so that is what can be done. End to end means that the original IP header is not required. Then in the IKE we learned two words, Oakley, which is the defilement part of the IKE, and ISAKMP, which is the protocol negotiation part of IKE. That's all. So there are two parts, two homeworks, two parts homework. Actually, both are very small. Actually, it turns out. One is for each field of IPv4, indicate whether it is immutable, mutable, predictable, and so on and so forth. And second thing is about the window. The replay window spans from 60 to 24. What will happen to packet 50, 100, and 150? Okay. Any questions about anything?